All right, good morning. Um, I'm gonna get started here. I got some bad news and some good news for you guys. The good news is I have successfully shared view only your exam one with you. So now you can go ahead and take a look at your own answer. The bad news is I forgot to set a fixed random key or random number seed when I generated the questions. So that makes it impossible for me to generate the keys for each individual test. So that's the bad news. So, so in light of the bad news, what I'll do is I am going to generate a full answer for a test that we haven't seen before. Okay, it's just a new combination of questions, same kind of questions, same kind of difficulty, and the same number of cases. Okay, so there are 9 questions, and of the 9 questions, there's a proportion of those of a particular type. So this key has exactly the same proportion, except everything is already answered. So I will share that probably in just a little bit. I got the markdown files already. I just don't have the HTML version of those files, so I can share that later. So that's what I would do. And meanwhile, we are going to continue to proceed and talk about predicate calculus. That's where we left off last time. All right, so let me see which tab. Got way too many tabs already open in the morning. All right, there we go. All right, so we're gonna have the relation homework opened up today. So let me do that first. You got about a week to do it, but don't procrastinate because this is one of those assignments where you probably want to get started as early as possible. And if you do have any questions, you'll let me know before the due date. So we'll make it due 1 week from today, which is the 12th. Okay, so we have October 12th at 10:30 a.m. Okay, so this one doesn't seem to work out. October 12th, 10:30. What did I type wrong? October 12th, 10:30 a.m. Oh, right. I can't even add. It's October 13th. I forgot to type the AM, and Canvas doesn't like it when things are not exactly the way it wants it. Okay, there we go. All right, so this is saved and published. So we got this due in a week. So get started as early as you can so that we have the next class on Thursday for you guys to ask questions. So I think that is pretty important. All right, so let's move on and continue to talk about propositional logic. So this is something that we started last Tuesday, because last Thursday was the test. So last Tuesday was the day that we started to talk about this. And there are 5 things that we introduced in propositional logic. Well, 4 things. So we got the alpha, the omega, the zeta, and also the iota. And I believe that we talked about almost all of them, except for, we also talked about well-formed formula. Okay, so let's go ahead and just recap those concepts. And let me do this here. I'm just typing, getting the note started on the side. There we go. All right, so it is not giving me. Oh, okay, I see. I got caps locked. So there we go. All right. So we talked about the 5 things. So we'll just kind of do a very quick review of the 5 things. The first one is alpha, which is uppercase A. It looks like uppercase A. So alpha is the set of symbols. Okay, and I'll put in parentheses that can be used as operands. Okay. Then we talked about omega. So it's uppercase omega. So uppercase omega is representing the set of all the operators. Okay, there we go. The set of all operators. And in propositional logic, sometimes these are also called connectives. But as far as we are concerned in computer science, these are known as operators. So we got and, or, that sort of stuff. I'll give you guys the examples in just a little bit. Zeta, Z-E-T-A, is the set of transformations. Okay, so these are rules, to syntactically transform one particular well-formed formula or a few well-formed formulae to a single well-formed formula that is known to be true. Okay, so we'll deal with this later. I'll give you guys some examples of what one of these rules may look like in Zeta. And then last but not least, we have iota. So iota is actually one of the most important ones. Well, I mean, they are all important, but without iota, the whole system is useless. So the iota is basically the set of all well-formed formulae known to be true to begin with. Okay, so these are the 4 sets that we need in order to use propositional logic. So now what we'll do is we're going to use an example here. So one example of an alpha is 0, 1. Typically we use PQRST for what we call variables, PQRST, and then we have the Greek letters theta, psi, and rho, and those are kind of special too. So we'll go ahead and type it here, theta, rho, and also psi. Okay. So this is just an example. Some other sources may use different letters, but that's okay. Okay, or they can use T for true, and then F for false instead of using 0 and 1. But it's okay. Now, the most important part is when we are looking at alpha, these things have no inherent meanings whatsoever. Okay, so the meanings are assigned a little bit later. Even 0 and 1 do not have meanings at this point. So omega, in this case, I'm not going to separate into omega 1 and omega 2. Omega 1 is the set of all the operators that only require 1 operand, and the omega 2 are the operators that require 2 operands. So we'll just go ahead and mix them up, into one single set over here. So we have negation, we have logical and, we have logical or, we have implication. Yeah, I know they don't look like the symbols right now, but they will. And then we also have equivalency. So these are the operators that we typically know of, and we know these guys. Zeta, on the other hand, is consisting of a whole bunch of rules. So I'll just kind of give you one particular one as an example. So the one that I'm going to give you, so every single rule in Zeta is a set, and then we have the kind of like a T but rotated counterclockwise 90-degree symbol, It is called V dash in LaTeX. So if you want to type that in any type of LaTeX-based typesetting program, it is known as a V dash. And then the other side would specify, the actual well-formed formulae that we want to formulate. Okay, so this is just one of those rules, and we'll go ahead and let's see what that. Yep, there we go. So I'm gonna go back and backfill. Okay, so I'm gonna go back and backfill what is inside the nested braces. So the nested braces is representing a set, okay, just like the outer braces are representing the delimiting portion of a set. But inside, okay, inside the nested braces, we are basically specifying and say, if you can find well-formed formulae that satisfy this particular pattern, okay? So when we specify pattern, that is when we use these Greek letters. The Greek letters are not variables. They are known as, there's a special name for those names, and I cannot remember. Well, I guess when we get to it, we'll talk about it. They're not variables. They're called schematas. There we go. So the Greek letters are known as schemata, and schemata symbols are only used when we need to specify rules. So we'll go ahead and take a look at the rule that we are just talking about. So let me move this right next to the module, so this way it's easier for me to remember where we are supposed to be at. There we go. All right, so let's just say that we know theta is known to be true. I think I got the... Okay, so let's say we know theta is known to be true, and we also know psi is known to be true. And what exactly is in theta? Well, we don't know. It's a placeholder. What do you know about, psi? We don't know either. It is a placeholder. So, but as long as we have one well-formed formula known as, theta is known to be true, and another one, we know as psi is also known to be true, then we use the transformation, and then we specify, hey, now we know this expression has to be true. What expression? It is simply theta and psi in this case. Okay, so this is how a particular transformation rule, or sometimes known as a production, is going to look like. The left-hand side of the symbol of the transformation or inference symbol is basically a set. Okay, the set specifies well-formed formulae in a particular format, and then on the right-hand side we have the result of the transformation. So that basically we are saying, if you give me two well-formed formulae known to be true, then I can tell you the conjunction of those two will be known to be true as well. Okay, I can give you another one. Okay, so the other one is probably a little bit more well-known. Okay, all right, so this one is really kind of funny, because you would probably normally say, okay, let me give you one that is kind of normal, and then I'll give you one that is not so normal. Okay, so this one involves implication. So we say theta implies psi. Okay, and that is tight. Oh, yep. So this is, theta implies psi. That's one of the formulae that has to be known to be true in order for this production to be useful. But now we specify another one. The other one is simply theta. All right. So now we are basically going through the entire system, and we're looking at everything that is known to be true. And then we ask, can we find two well-formed formulae to fit into this particular format? In other words, we're looking for an implication, But in addition to the implication itself, we are also looking for the left-hand side of the implication on its own, also known to be true. So if you remember in an implication, if the entire implication is true, then we got a few scenarios. Either if the precedent, which is the left-hand side, if theta is false, then the whole implication is true. Okay, that's not very helpful. But we also have one special case. If the left-hand side is known to be true, which is what is happening here, and the implication itself is also known to be true, then we also know the consequent, which is the right-hand side of the implication, is also known to be true in this case. So this particular production will now basically say, oh, if you can find me, something that is an implication, and then the precedent, which is the left-hand side of the implication, is also known to be true, then we know the right-hand side is also known to be true at this point. So this is another example of what a production may look like. And I'll give you one more. This other one that I'm going to give you is going to look pretty confusing. Okay, so it has an empty set. Okay, so the braces are here, and I'm not going to fill in anything between the braces. So this is really specifying an empty set. So now the question is, oh, I used the wrong symbol here because I should not be using right arrow. Right arrow means implication. I'm supposed to use V dash here. So V dash is a syntactical operation. Right arrow implication is a logical operation. There's a difference between the two. So this time I'm using a V dash, which is the syntactical resulting inference symbol. So what can I infer from nothing? Well, as it turns out, I can infer quite a few things. I can pick up any well-formed formula. Okay, let's call that theta. So what I can do is I can say, well, I really don't know whether theta is true or not. But guess what? I can do something like this. I can say between theta and not theta, one of them is going to be true. At least one of them is going to be true. So this is what, this is an example of three productions or three transformation rules that is usually found in Zeta. Do we have any questions about, what a transformation rule looks like, or what they do? Any questions? All right, so it looks like we don't have any questions at this point. All right, so now we need some seed. So I'll go back and talk about what is a well-formed formula, because we talked about it last Tuesday, but it has been a week already. So I'm going to go back and kind of hit on the main points. So iota this time is really important because last time I never gave you an example of what is in iota. This time I'll give you one. These are the well-formed formulae that are known to be true for no particular reason. Okay, these are just axiomatic truths. So I will say one is true, and I will say not false is true, and I can also name a few things that are known to be true as well. So it depends on what the system is trying to represent. So the rest of what is known to be true really depends on what the system is trying to represent. And I'll give you an example in just a little bit. But in this case, I'm just giving you an okay. So we got a question from Omar. So for individual elements in Z on the left-hand side of, I guess, the V dash symbol, does everything in the braces have to be true for the right-hand side to be true? Yes, but it's okay. The answer is yes, but we have to be careful because it is specifying a placeholder. So theta, psi, and sometimes rho, they are representing placeholders. In other words, it's almost like a regular expression kind of thing. We're specifying a pattern, and we're asking, can we find something that fits this particular pattern? Now, it is entirely possible that all the well-formed formulae known to be true, none of them will fit the pattern that we specify on the left-hand side of the V dash symbol. Once again, the V dash symbol is the T that is rotated. Then we cannot use that production rule. Okay. Yes. So that is why iota is important, because iota gives us the initial well-formed formulae known to be true. So from omega, then from iota. Okay, I meant to say iota. So iota is the set of the well-formed formulae known to be true to begin with. That is what we can start to use. Zeta, the transformation rules in zeta can start with whatever we have in iota. All right, cool. I'll give you guys an example of what is typically something that people do with a propositional logic system. Okay, so in this particular case, I can just randomly pick something like P implies Q is known to be true, and we can also say Q or R is known to be true, that sort of thing. Okay, and then we can say S and T is known to be true. Now, don't ask me why that is the case. That is these are just known to be true to begin with. So that's why iota is so important, because it really is trying to tell you what the truth is. So I can give you an example. Okay, let me just kind of give you an example here. So if I say P as a variable is representing text classes boring. Okay. Now it is a variable, which means it can be true. It can also be false. The next one is Q. Okay. We'll say at least one person falls asleep in a boring class. Okay, so given a boring class, at least one person is going to fall asleep. Not that I can really tell these days, because we are online, right? And then we'll have another one. Let's just say PQR. Okay, so the next letter is R. So we'll say R means saying falling asleep helps is restful. Okay. All right. And let's see, what else should I put here? Okay, and PQRST. Yes. Okay. So the next one is at least one person feels rested. Okay, there we go. Now, the one important point about propositional logic is inherently it cannot deal with quantifiers. So that's why the quantifiers are not explicitly expressed using for all and there exist. Each variable is including a quantifier on its own. Okay. All right. So these are the variables, which means that each one can be true, each one can also be false. So given these are the variables, I'm going to change iota in this particular case. So we'll just go ahead and say text classes are boring, and okay, so we can go for some implications. So we can say Q and R implies S. Oh, I can't do this because the quantifiers are kind of messing up things. So we should probably not say at least one person falls asleep. And okay, there we go. There we go. Okay, so I see that. All right. So in the iota, we'll say it is true that R by itself is true. Okay, if falling asleep is restful. Okay, and then we'll go ahead and use the other one. It's going to be an expression. So the other one would say P and Q implies S. Okay, and I need to close the braces. There we go. And something is not right. Oh, okay. There we go. All right. Nope, still doesn't like it. Got too many open dollar signs. Now it looks good. All right, so let's take a look at this iota. So this iota says, we are by default assigning a meaning to the symbol 1. Okay, the symbol 1 basically is known to be a constant that is representing true. Okay, because everything in alpha by itself is a well-formed formula. The second one is the negation applied to false is also known to be true. So before we put this item, before we get to iota, 0 is simply a symbol. It has no particular meaning. And then the negation operator is known to be a single operand operator, but it also has no particular meaning. But this is where we assign the meaning to not false. Okay, not false is an expression that is known to be true. R itself is known to be true, and then P and Q implies S as an expression is known to be true. So, but this system is not particularly useful because there's not really a whole lot of inference we can do in this particular system. So I think I need and R over here and R over here. All right. In order to do some inferencing, we'll need a few things. So if we say S is known to be true, then there's a bunch of inferencing we can do. Okay, we can make a conclusion, about P and Q as well in this case. Do we have any questions about the what each set is representing in a propositional logic system? Alpha gives us basically just the basic symbols, no particular meaning assigned to any one of the symbols. We do have 3 groups, 0, 1 are constants, so they are not supposed to change the values. P, Q, R, S, T are known as variables, which means, each one by itself, unless they appear in iota, each one can be true or false. And then we have the Greek symbols. In this case, we have theta, rho, and psi. So those are called schematas. In other words, they can only be used when we express a transformation rule. Because in a transformation rule, we need placeholders instead of exact specific well-formed formulae. Does anyone want me to go over what is a well-formed formula, or are we okay with that concept already? Okay, no particular request. All right, so I'm just going to make the assumption that we are All right. So with all of these things in place, let's go ahead and take a look at what people do with a propositional logic system. So what people do with a propositional logic system is we use it to prove theorems. Okay, so we use okay, I just typed in the wrong window, so it pulled the box out of here. There we go. Okay, so now I'm at the right window. So people, meaning human beings, use a propositional logic system to prove theorems. Okay. So what do I mean by a theorem? So let's use this example here. Okay, and let's use this as an example. We have alpha that looks like this, omega that looks like this, zeta that looks well. Okay, so we have some hidden rules. Okay, so I'm gonna cheat a little bit here and not fully specify the hidden rules. So we'll go ahead and say, okay, so let's say tech claims, okay, that P and Q and R, oops, wedge, there we go, is true. Okay. So, but this is just a claim, okay? I'm saying that a particular well-formed formula is true. But how do we know it's true or not? Now, this is relative to the example that we have just been using here, okay? So relative to that example, tech says, I think this expression here is true. But of course, you guys do not know whether it's true or not, and you go like, okay, tech, you have to prove that it is true. So now we have to look at a propositional logic system, and we have to basically apply the transformation rules in order to see if we can somehow end up transforming into P and Q and R so that it is true. Okay. And of the given rules that we have here, none of these is going to help, okay? Because I have not specified enough transformation rules to prove that P and Q and R is true, given that these individual facts are true. Okay. In fact, I can basically go back to my claim, and I can just say P and Q is true, okay? Because R is already known to be true. There's no need to specify that. So if you prove a theorem, okay, by hand, you basically have to start with whatever is given to you to be true, and then use the transformation rules, and then hopefully at some point you end up with this one single well-formed formula, and you go like, oh, okay, now that is true. Does everybody sort of understand what I'm talking about? Yes? No? Maybe? I don't see any response. Okay. Okay, Alex is typing something. We are doing a tree like last time. I'm not sure what you mean by a tree like last time. This time I think is unique because we have not used transformation rules before. So this one is unique. Oh, okay. All right. All right. So let's ignore that we're in a propositional logic system and try to prove this, just using, okay, we'll first use common sense, and then we'll go back and use Boolean algebra, and then we'll go back and look at what transformation rules are missing in this case. So we'll go ahead and start using the wrong window for typing. So we'll go ahead and try to prove using an intuitive approach. Okay. All right. So using the intuitive approach, we look at what is known to be true. So we can see that S is known to be true. We can also see that this implication is also known to be true. So if S is true and the implication is also known to be true, that is not sufficient to prove that P and Q are true, because they can be false and this entire implication is still true. So I need to add some additional things to what is known to be true in order for, oh, that may not be doable because of the implication. So I'm going to flip this around a little bit. So I'm sorry that I have to change this. So I have to change this around a little bit, and instead of knowing that S is true, we'll just say that, let's just say that S is known to be not true. Okay, and then we'll see what we can do about this. If S is not true, then we can actually infer a few things. We can infer P or Q is false. Let me think about this a little bit. Because R is known to be true, so P and Q has to be false. So not P and not Q. Not P or not Q has to be true. Okay, so I'm going to add it here. Because the other one is actually not provable, but this one is. And we'll deal with the question of what do we do about theorems that are not provable. So I'm changing things just a little bit. Instead of saying S is true, we are saying S is not true, which basically, because of the way I assign meanings to PQRST, it's basically saying, it is not true that at least one person feels rested in text classes. Okay, that is known to be true. Not at least one person feels rested in text class is known to be true. So now tech is saying, well, I think not P or not Q is true, which is basically saying text classes are not boring, or it is not the case that at least one person falls asleep in a boring class. Okay, so I'm claiming that not P or not Q is true. So now we want to prove this just kind of intuitively. And then we'll go back and specify the rules that we need in order to complete the system, so that we can actually use production rules to get to the result that we want. All right, so the first thing has to do with implication. So let me just kind of give you a general sense of implication. So this one is, I should not use the symbols that we have introduced so far, because this is just kind of like an off-topic discussion. So if I say X implies Y, okay, so we'll just stare at this for a moment. And I tell you that this is false. The implication is false. If I say that this is false, okay, no, I shouldn't say that. I tell you that this is true, okay, so X implies Y is known to be true. And then on top of that, I also tell you that Y is false. Okay, what can you deduce from just these two facts? Okay, first of all, X implies Y is true. The implication itself is true, and Y is false. And Omar is close. Y is false. Oh yes, so Omar is right. Okay, so Omar is 100% correct in this case. X has to be false. Okay, and so I'll say as a result, X is false. There's no, x cannot be true. X has to be false. So let's go ahead and look at this result here, because I want to be able to at least prove this using a truth table, and then we'll go back to our discussion. So let's go ahead and take a look at a truth table and see why that is the case. And to get a truth table to work, we need x as a variable, we got y as a variable, and then we have x implies y as another column. Okay, this time it is an expression. So we have x implies y as an equation. So to generate the table, I need that. Okay, so now I'm typing on the side in Markdown to generate the table. So x and y are independent variables. So when x is false, y can be false, or true. And then when x is true, y can be false or true. Okay. So now we want to look at the expression x implies y. So we have seen this already. This is this is a definition that we have already gone through. Whenever x is false, or whenever the precedent of an implication is false, the entire implication is known to be true. All right, so that takes care of two rows automatically. When the precedent is true and then the consequent is false, that is the only time for an implication to be false. When both are true, then the implication is also true at the same time. So let me just kind of reformat x so that it looks consistent with the font, the choice of font, above. So there we go. So do we have any questions about the this particular truth table, which is basically just a recap of what implication means? Okay, I'm not seeing any questions. All right, so assuming that we don't have any questions about this truth table, which is the definition of implication, okay? This is one way to define implication in Boolean logic or Boolean algebra. So when you look at this and go like, okay, so what does it mean if x implies y is known to be true? So that means we can ignore this row here because we know that the implication itself is true. Okay, so knowing that x implies y is true, we only focus on the first row, the second row, and also the last row. So now we say, oh, but guess what? There's one more thing we know. We know y is false. Y is 0. So of the 3 rows that we narrow down, which is the first, the second, and the fourth, of these 3 rows, only one has the implication being true and y being false, because those 2 things are given to us. So there's only one thing we can say about x in this case. We can now say that x has to be false. That is why, as a result of x implies y itself, the implication being true, and also y being false, we now know that x is false. Is that okay? Does everybody understand, why we can make that deduction? Not seeing any questions. Okay, so we are good. All right, cool. All right, so now we go back and say, this seems like a good thing to be captured in the transformation rule so that we can add one more entry to zeta. Okay, so instead of repeating the whole set, we'll just go ahead and say, oh, this thing, by the way, is an element of zeta. So we'll start with that. So we'll start with is an element of zeta. Okay. So now the question is, what is an element of zeta? Okay, it's a transformation rule. So knowing that it is a transformation rule, that we know that it has a v dash operator. Now the question is, what is on the left hand side and what is on the right hand side? What is on the left-hand side is always a set. Okay, the set is now specifying one or more or zero. Okay, well-formed formulae, but together the set has to define a particular pattern. So this time, we're gonna say theta, oops, backslash theta implies psi is one of them, and then the other one is the negation of psi. So what this means is go through all the well-formed formulae, either known to be true from iota or as a result of earlier application of any rule of zeta is now known to be true. Let's look through all of those well-formed formulae. If I can find one implication, okay, then I will define the left-hand side, to be that whole thing is known to be theta. I'll look at the entire right-hand side of the implication and look at that as psi. Now I go through all of those well-formed formulae again, but this time I'm looking for the negation of psi by itself, to be in the well-formed formulae known to be true. If that is the case, now I can infer one thing, because what I can infer in this case is the negation of theta. Is that okay? Does everybody understand why this rule is handy to be in zeta? Because it corresponds to logic. Are we still doing okay at this point? Okay, Omar is getting it. All right. So this is one. Okay. So now we need to look at some more. So we'll look at De Morgan's law. Okay, so De Morgan's law is handy to have, in this case. So we'll go ahead and encode De Morgan's law. And I think De Morgan is spelled as one word. I cannot remember. Let's check. Yep, 2 words. So I was right. Okay, very good. All right. So now we want to define De Morgan's law. So the first thing is, okay, what does it look like in De Morgan's law? There are 2 laws, that we need to specifically talk about. The negation is always on the outside of something, and then inside, once again, I'm just going to use XYZ, which is just to make sure that we do not confuse what we know in Boolean algebra with what is in the propositional logic system that we are talking about at this point. So if you negate an and, okay, x and y, if you negate an and, then it really is the same thing as the negation of the first item or the negation of the second item. So this is one of the laws of one of the 2 De Morgan's law. The other De Morgan's law is exactly the opposite. We change this to an or, and then we change that to an and. That is also a part of De Morgan's law. Okay. Now, how do we know each one of these work? Once again, we can use truth table. So this time, when you create a truth table, you keep the first 2 columns because x and y are supposed to be independent variables. So you still have the first 2 columns being the same, one for x and one for y. And then this time you have to create 2 additional columns. One column is the one to the left-hand side of the equality symbol, and then the other one is the one to the right-hand side of the equality symbol. And then what you want to do is to look at the truth-false value of those 2 columns corresponding to the expressions and make sure that they have the same value on every single row. And you will find that they do, okay? And that's why we know that you can rewrite a negated and as an or, but this time we move the negation to each item that we were originally anding. Or if you have a negation that is done after a or operation, then you can transform that into an AND operation, but this time we apply the negation to the items that we were originally ORing. Okay, so now the question is, so how do we transform? How do we encode this into the transformation rules? Well, as it turns out, it's really simple. Okay, so the rules that we want to capture in Zeta is really just replacing, just syntactically changing a few things. What it's going to look like is, okay, we cannot refer to x and y anymore because remember, x and y are not in alpha. So we have to change these to the Greek symbols. One is, I'll just pick a theta and a psi in this case, and then we'll correspondingly change the theta and psi over here. Okay, and get rid of the y. There we go. All right. Oh, you cannot. I made a mistake somewhere. There we go. An extra space before the dollar sign. Okay. So, but this time we also do not have an equal. We have a v dash symbol, and we also want to change the left hand side to be a set. Okay. Now this time the set only has one item, which is perfectly okay. There's nothing wrong with that. And now we say this is in Zeta. In other words, we look at something that we see in as an axiom in Boolean algebra, and we just transform that into a transformation rule in propositional logic system. Now that is not entirely correct, because the other way around is true as well. So I'm just trying to find a quick and easy way to do this. Maybe not a so quick and easy, but I'll just gonna retype it. So the negation of theta or the negation of psi, and put that in a set. So I'm just editing a little bit here, and then we put a v dash over here, and then get rid of the set notation on the other side, and then the rest we can get rid of. There we go. This is also in Zeta. Yep. There we go. So we need to, because given this side, we also can go the other opposite direction to say that, oh, it's the same as this. Does everybody understand why one single equality in Boolean algebra as an axiom breaks down to two rules inside Zeta? Any questions about this part? All right. It has to do with this equal symbol, because the equal symbol is really the same thing as if and only if. So if this is saying if and only if, that means it has to go in both directions. Okay. So you can probably imagine what we need to do for the other De Morgan's law. Basically, we create two rules, one to go from this side to this side, and then one from going from the right hand side back to the left hand side. So once we have De Morgan's law, we look at the equation or the problem that we are trying to solve. We go like, we're almost there, because we can now say that because not S is known to be true, and this implication is also known to be true. Once we apply the first rule, then we end up with the negation of this to be true. Okay, so if the negation of that is known to be true, then we can apply De Morgan's law, so that we end up with not P or not Q or not R. But since R is known to be true, then we have a not true, which is a 0. So we can now we can have simplification rules, which basically says anything or false is just at anything itself. Okay, so let's go ahead and specify that rule over here. Okay, so we can say this is one simplification rule. Okay, one of the simplification rules. There are many. This is just one of them. So this one says, if you give me something that looks like whatever theta is, theta, and it has a or 0 or false in it. Okay. Oh, that's easy. Okay. We can immediately say, hey, we can just simplify this whole thing to theta. And we'll say that this is a transformation rule that is supposed to be in our zeta. Okay, does everybody understand what this rule is saying? Or why that is the case? If you give me any disjunction, and I don't really care about the part that is not the 0, but if you can identify that one of the components that we are ORing is a false, then we can say, hey, that doesn't need to be specified in the OR. Does everybody see how this happens? Yes? No? Okay. Omar is typing. All right, so go ahead and ask, Omar. So the implication thing earlier, so I'm going to assume we are talking about this one here. Yeah, go ahead. You can ask. Go ahead and ask. So the implication itself, it doesn't have to be in iota itself, but it has to be transformable from the well-formed formulae in iota. Because we can create implications from other operators. Okay, so the next question is, are the well-formed formulae that formed from combinations of alpha and omega not in iota? Okay, so that's a very interesting question. Okay, let me use, okay, the best way to do this is to use a graphical example, and since I'm not in the tablet mode, I'm going to use a tool. Let me see if I can use that tool for this purpose. I'm just thinking about what tool I want to use. It's going to be a graphical tool, and I think Inkscape may be usable in this case. And let me resize the Inkscape window. Oh, where is it? Here we go. And maximize. All right, so I just have to make it fit into the window that we have here. There we go. All right, so this is Inkscape, and it's just a little tool that I use to draw pictures. So I want to do a zoom control first. There's the magnifying glass. I'm not used to Inkscape in this small of a window. The magnifying glass should be somewhere. All right. Usually it is the first one of the few items on the top. All right, so let's check. Uh-oh. Okay, Discord just crashed. I'm just restarting it. Here we go. All right, so we are back. Here we go. All right, so Discord just crashed. I'm going to reshare the screen. There we go. All right. And I was trying to find the zoom tool so that I can focus on just a smaller region on the screen. And apparently the tools have changed a little bit, or at least the location have changed a little bit. Oh, right there. There we go. Okay. So this is the zoom tool. There we go. All right. So let's go ahead and imagine that this entire thing, okay, I'll be more specific about what this entire thing is. So we'll go ahead and say that this entire rectangle is representing the space of all the well-formed formulae. And to make this more effective, I'm gonna fill this entire area with a color. So we go to fill with a blue color. Okay. And we want to saturate, and we want it to be blue. There we go. Dark blue. There we go. That's a nice blue. All right. So we look at the blue area, and we say this is the entire space of well-formed formulae. Okay. So every single pixel, okay, that is blue, is a well-formed formula. Okay. So what iota is specifying things that are kind of little dots on this in this entire space. So we'll go ahead and make tiny little dots. I suppose I can use circles for that. So we'll go ahead and draw some circles. And each circle is going to have a red color. There we go. All right. So this is basically one well-formed formula that is in iota. Okay, and we can, basically have a whole bunch of these. So let's just say that this is it. So iota in this case, in this particular example, has 7 elements. So those 7 elements, which are represented by the red circles, they are well-formed formulae because they're inside the blue triangle. But these are the only ones known to be true. In other words, we're using the color red to indicate what well-formed formulae are now known to be true. The stuff in iota are initialized to be true, so we don't even ask, why are they true? So now we want to look at transformation rules. Transformation rules are basically saying, hey, if you can match this pattern, then that other pattern would also be known to be true. If a well-formed formula, if a whole bunch of well-formed formulae meets the syntactic pattern matching inside the set notation on the left-hand side of the V dash symbol, if you can find things that are already labeled red to meet this requirement, then whatever is on the right-hand side of the V dash should also be labeled red. That is what a transformation rule is trying to say. Okay, so that means, okay, let me just make a copy of this one. Okay, so these 7 are the initial ones. So now I will make new ones. And the new one that I make, I will label those things in yellow. Okay, so the yellow ones are not in iota, but they are known to be true nonetheless because they can be transformed from something that is either labeled red already or labeled yellow already. So now if I want to be fancy about this, okay, I can add a connector, I think. No, yep, okay. So if I make connectors, no, I suppose I cannot do that here. I'm trying to draw arrows. So the other way to draw an arrow is really just to use a line tool. Okay, there we go. So if I were to draw a line tool, let's say this is transformable into this one using one of the transformation rules in Zeta. Okay, so now we have a line, and to make this easy to read, I will go to stroke pane and make this, oh, I don't know, green is probably good. Fully saturated and high value. And because it's a stroke, we can also specify the markers. So the end marker is going to be an arrow like that. There we go. So the green arrow is basically representing an application of one of the elements in Zeta. Okay. Now, sometimes you need several things to make a new one. So let's say we need this guy and this guy in order to make a new one. So now we draw another one like this. Okay. There we go. And then we make this one point to here as well. And then we can select both of them in order to apply the change of colors. So we'll make it green again, saturated all the way to green, and specify the arrowhead like so. So now we say, oh, there's another well-formed formulae that is supposed to be here, and it's going to be yellow in color as well. So I need to somehow select the yellow one. It won't let me do it. Okay, so we'll do it the hard way and move this one over here, and then change the color back to yellow. There we go. All right, so why is it not changing? Oh, okay, I'm changing the stroke paint. I'm supposed to change the fill color. There we go. All right. So in this picture, now we have 7 elements from IOTA. Those are the 7 ones that are labeled red. So those we don't ask why they are true. They are given to us, and yes, these things are known to be true. Then we have 2 yellow ones. Okay, the 2 yellow dots, each one is representing the result of applying one of the transformation rules. This particular yellow one is the result of applying the transformation rule represented by the green arrow based on this red dot here, which is one of the well-formed formulae in the IOTA set. The other yellow dot, which is over here, on the other hand, is the result of the application of another rule in Zeta. But that particular application requires 2 elements in order to match the left-hand side. So it is actually using one of the results of a previously applied transformation rule, and one of the things from IOTA itself in order to come to this conclusion of, hey, by the way, whatever blue dot that was originally here, now we know that is true as well. So is this helping to explain the relationship between the elements in IOTA, all the well-formed formulae that can ever be formed based on alpha and omega, and the role of the transformation rule? Cool. So the idea, okay, so just using this particular picture, so the idea is the theorem that we are given is basically a dot in this entire picture as well. Okay, so I am going to make another dot all the way over here. And this one is going to be, has zero saturation. So it's just a white dot, or make it gray, okay? So we'll make it a gray dot to emphasize that this is the theorem. In other words, we don't know whether this is true or not, okay? We really don't know whether this particular point over here is supposed to be true or not supposed to be true. That's the question, okay? So the question is now saying, can we somehow use these green arrows, okay, which are representing the application of the rules in Zeta on things that are already labeled either red or yellow. So you can see the yellow dots would increase, right? Because every single time we apply one of the rules in Zeta, we are basically creating more and more, or we are labeling more and more well-formed formulae to be yellow. So eventually we end up with a lot of yellow dots, okay? The question is, can we somehow label this dot that is gray, representing this is one thing that we're interested in? Can we end up labeling this thing as yellow eventually or not? That is how the system is supposed to prove a theorem. All right, so Omar is typing on the side and says, so iota contains the given and does not expand per se. Right, so the red dots do not expand by themselves. The expansion has to do with the application of the rules, which are represented by green arrows in this picture. So let me just kind of explain the whole thing again, okay? The entire space, the entire space is representing all the well-formed formulae that can ever exist, given what we have in alpha and also what we have in omega. In other words, we're talking about every single sentence that can be grammatically correct in this case. Okay, many of those are meaningless. Okay, but nonetheless they are grammatically correct. And then the red dots over here are the things in iota. Now, every single element in iota are well formed. Okay, they're all well formed formulae, and that's why they're in this space. But they are labeled red in this case to emphasize that these things are known to be true. Don't ask me why they're true. There will be no explanation of why they are true. They are just given to be true because they are elements in iota. Now, starting with everything that is known to be true, or the red dots, now we will see whether the rules in Zeta can be applied. Now, it's possible that one particular red dot can only have two green arrows coming out of it, and some may have six coming out of it. Some may even have more coming out of it, and some may require multiple dots already labeled either red or yellow in order to create another yellow dot. But the idea is, as we apply the transformation rules in Zeta, we'll be labeling more and more and more of these dots yellow. The question is, the theorem that we are trying to prove, which really is just a dot, okay? The theorem is really just a well-formed formula itself in the entire space. The question is, can we somehow label the theorem yellow as well? That really is the question. Okay. I'm looking at the time. We got 5 more minutes, but this is a good time to talk about a problem with this way of approaching theorem proving. Do you think this representation of the blue space is realistic? In other words, is this space finite? Given a particular set alpha, let's just say the alpha itself has finite elements. Okay, it has got 0, 1, p, q, r, s, t, theta, psi, and rho. Definitely finite. Omega is also finite, right? Omega only has negation, conjunction, disjunction, implication, and if and only if. Exactly. The space is infinite. Why is it infinite? Because if you are just looking at things that are syntactically correct, so I'm going back to the browser. Okay, not this one. this browser, and I'm just giving you well-formed formulae at this point. Okay, so I'm scrolling down to an empty space right here. Okay, WFFs. Okay, well, we can do something that is simple, right? Because we can say, oh, okay, P and Q looks syntactically correct in this particular example, so it is a well-formed formula. Okay, not a problem, right? But that's pretty easy to understand. P by itself, okay, so we don't even have to look too far. Okay, we can just look at P by itself is a well-formed formula, and that is by definition, because every single symbol in alpha by itself is known to be a well-formed formula. Okay, now does that mean P that does it mean P as a variable is true? No, it simply means it is syntactically correct, okay, as a well-formed formula. Now, but if you go back to one of the production that we have already seen, which is okay, the cursor on in my editor is tied into the cursor in the browser, and that's why sometimes it doesn't want to move along the way I want it. Okay, so look at this production here. This production, all it says is from absolutely nothing. Okay, any well-formed formula theta or the negation of itself is known to be true. Okay, so now we can just, without knowing anything in iota, okay, without knowing what well-formed formulae are in iota, now we can start to spew nonsense, right? We can now say, hey, we know P or not P is a well-formed formula. Not only is it a well-formed formula, it is known to be true. This thing is going to be labeled yellow without having any connections to other yellow dots or red dots. Okay, if we can just suddenly start to label a whole bunch of things to be yellow. Now, to make this worse, okay, we can now use P or not P as theta itself, and then reapply the same rule. So the result of reapplying that rule is to say this entire thing, or the negation of itself, which is P or not P, is also going to be labeled yellow. Is that okay so far? And if you are not convinced that the space of all the well-known, the well-formed formulae is infinite, let's go, like a few steps further. Okay, to take this a few steps further, it is going to be helpful if I don't know whether Markdown would like this or not, so we'll give it a try. Nope, it does not like this. Alrighty. Okay, so I guess the way to do this is to do a bunch of editing here, delete a whole bunch of stuff, and then joining two lines. Okay, so just bear with me as I join the two lines. So, or the negation of that is also a well-formed formula. I think I need extra parentheses just to. Okay, I need extra parentheses from here all the way to here. There we go. Is everybody kind of following, what I'm trying to do, or what I'm trying to show you guys? Is you can reapply the same rule, and we can now label, not only are we expanding the entire space, we are actually creating an infinite number of dots that are yellow. Now the question is this going to help me prove the theorem, get to that little gray dot that I want to see whether it can be labeled yellow or not? Absolutely not, right? So we have two problems, okay? Today it's important for us to make a conclusion of the two problems that we have. So the two problems that we have with this kind of propositional logic system is, one, that space is infinite. In other words, realistically speaking, that red, the blue component is infinite. It stretches out to infinity. So our space is infinite to begin with. And some people say, yeah, but we deal with sets that have an infinite number of elements all the time. Integers is one, natural number is the other one, and we have this really cool thing about having aleph null. Okay, so by itself doesn't seem to be a problem. The second problem is we don't know whether the theorem that we're interested in is true or not. Okay, so let me just rephrase this in a way that everybody understands. I hope you have heard of the term or the phrase of finding a needle in a haystack. Yes? Okay, so if okay, cool. I just want to make sure that everybody knows about that phrase. Okay, very good. So finding a needle in a haystack. Okay. So theorem proving is to basically say, okay, I will show you this needle over here. Okay, I'll use a prop. So look at the video portion of the screen. So I'm going to use this as a needle, and I say, hey, this is the needle that I'm looking for. Can you go through the haystack and come back and make a conclusion of whether this needle is in the haystack or not? Okay. So normally, okay, if you have a like a normal haystack and a normal needle, it's not a big problem. It's very tedious, right? Because you're trying to that's what the whole phrase is supposed to mean is, oh, this is going to be tedious, okay? Or it's going to be difficult, but not undoable. But imagine the haystack to be an infinite haystack. In other words, there's no end to that haystack. So now we have a big problem. The big problem is because after 6 days, you come back to me and go like, Tech, I still haven't found that needle that you asked me to find. And I say, but that's not an answer. Because the question that I was asking was, can you find this needle or not? And you're coming back and say, I still have not found it. That is not an answer that I would say, yep, okay, that's exactly what I was looking for. Because it's not possible, okay? You can go for years and years through the infinite haystack, not being able to find the needle, but you cannot differentiate between two situations. The first situation is the needle was never in the haystack. In other words, the theorem that I was asking you to prove is not really a theorem, okay? And that's why you cannot prove it. But it is also possible in scenario 2 that you just haven't gotten to it yet. And it's impossible to differentiate between these two. And as a result, when you're trying to prove something and you're heading out in the wrong direction, like what I'm intentionally doing here, using the wrong production rule, using the wrong element in zeta to expand to create more dots, that are labeled to label more of the blue dots as yellow. You can go for years and years and years, and it doesn't make any progress toward the gray dot. Okay, so now we have a problem. Okay, because in human terms, when you're doing a proof example in a math class, well, I'm hoping your math professors are not tricky and give you a theorem that is not provable, or it's not actually a theorem. So so that you spend the entire weekend going like, oh, I cannot prove this. Okay, but you cannot tell whether you just haven't spent enough time, or the professor is trying to trick you and say, hey, this is actually not a theorem, but I would like to see you guys give it a try. Okay, that is the problem that we have with this type of transformation or this type of propositional logic system, is that the space is infinite. You can try it. Nope, that's not possible, because a theorem, okay, an expression not being a theorem doesn't mean it is false. It simply means it does not follow what is known to be true. There's a big difference between those. Okay, in other words, Um, if I say A and B are known to be true, those things are in iota, and now we have C, which is another well-formed formula, and I say, well, is C a theorem? Okay, what I'm really asking is, does C follow A and B? Okay, it doesn't mean that C is not true. It simply means C is not following A and B. Okay, so there's a big difference of trying to prove that A and B implies C as opposed to showing that C is false. It is not, those two things are not complementary to each other. Okay, so now we run into this big problem. Okay, and of course, if we are having problem with this system, the computer is going to have even a bigger problem with this, because we have experience, and we kind of usually go like, okay, we have some rules of thumb, and after taking math classes for 4 or 5 years, I have some techniques that I can use, and blah 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 blah. Okay, the computer has no such domain knowledge. Okay, it would just really just go to try to prove something. So um, on Thursday, okay, so let me just go back to the notes here. So what we're doing on Thursday, let me go back to the overall here. So on Thursday, we'll get to section 5. Section 5 is interesting because it is a way to look at every single possible well-formed formula, okay, using the operators that we are familiar with, like negation, conjunction, disjunction, implication, if and only if, that sort of thing. And we boil everything down to what we call a CNF, okay, which is conjunctive normal form, okay. So the first part is to say, yeah, give me any weird looking but syntactically correct Boolean expression, and I can transform that, okay, into a very specific awkward format called CNF. That's the first part. And as it turns out, given a fixed number of constants, variables, and operators and whatnot, that space is actually contained. It is finite. Okay, it is still pretty big. Okay, I think it's big O of I think it's the cube of number of symbols or variables. It's sort of big. Okay, but the point is it is finite. Okay, now it's a big problem. It's we have just solved one huge problem, because instead of trying to look for a needle in an infinite haystack, it is a finite haystack now. You can systematically go through the haystack and conclusively tell me that the needle is in there or not in there. Okay, so that's the first thing. And then we have resolution, which is section 5.1. So resolution is also very interesting, because instead of having like 20 or 30 elements in zeta, which resembles how people solve Boolean equations, how we prove Boolean expressions, there's only one transformation rule. So imagine that, right? Because instead of having like a whole bunch of stuff, oh, okay, De Morgan's law takes up 4 entries by itself, okay? Then you have distribution, which takes up also 4 entries. And then you have, and this is not even to count, all the other things, the simplification rules and whatnot. So to do it the human way, is to say, okay, I can't even remember all of those rules because there are too many. But using resolution, there's only one rule, okay? There's only one rule. The space is finite, right? So that makes it very, very easy to mechanically prove a theorem, okay? So that is something that we'll be talking about on Thursday. So the important thing that we want to do today, okay, between now and Thursday, is 1, to get started on the relation homework assignment, okay, and 2 is to really just to fully understand what we have talked about today. Not so much the symbols, okay, but what it is representing, okay, the way that we do things. And if we try to translate how we do things to the computer, we have a problem, okay, because it's not solvable. So that's why, and that's why we have resolution and all the topics in section 5 because those are the mechanisms that we can rely on in order to come to a conclusion after a known amount of time, and basically say, guess what, Tech, that expression that you gave me, that's not a theorem. And you can come to that conclusion in a fixed amount of time, in a known amount of time, which is great because now I can say, okay, here's a problem. Okay, is this expression a theorem of relative to this iota that I have given you? And within a fixed amount of time, the computer can come back with a conclusion of yes or no. Okay, so that's kind of the stuff that we'll be talking about on Thursday. All right, so I am running out of time today, and I will see you guys on Thursday. And hopefully more people can join us on Thursday because we only got a few today. Yeah, no row today. So let me just type here. Yep, no row taking today. All right. So I will stay online for my office hour between noon and 1 o'clock. So you guys can stay here, or you can, do a private check if you want to. But I will get off of the voice channel, but I'll pay attention to the text channel in case of any questions. So have a nice day. I'll see you on Thursday.